All right, pre-calc section 1.2, part 3. All right, when we take a look at this example number 74, okay, or 71, we're still just trying to simplify things. X to the 8 divided by x squared. This changes to everything's the same except the x is now to the 6th power on top. 8x squared on the bottom is gone. Now, an interesting part of this is if you have a root, you really want to, I want you guys to be able to tell me how to make it so that it's a fraction with a completely non-root denominator. See, right now, this is what's happening. You've got the 4th root of the top, which is 5 times x to the 6 times y cubed, divided by, I broke up the roots fraction into 2 roots, on the bottom. The 4th root of 27 is not like a perfect something to the 4th power, all right? What we need to do is figure out a way to make it so that that number is nice and neat. Now here's where you guys do some investigation. You ask yourself, can I break down 27 in any way that makes it so that we get 4 of a kind? All right? So we're actually pretty close. Because 27 is 3 times 3 times 3. The reason why that's helpful, I'll just kind of replace it as we see it here, is that if I multiply the bottom by one more 4th root of 3, which I also have to do to the top, any 4th root quantity times another 4th root quantity can be combined. So it's sort of like saying, hey, this is the same as the 4th root of 4 3's multiplied together. Which makes it 3. So the bottom is now 3 if I multiply the top and bottom by the 4th root of 3. So the bottom of this fraction, as simple as they come. The top is going to now be, okay, it's kind of like we can combine these two. You're going to have a 4th root of 15. But take into account the fact that, hey, the 4th root of x to the 6, I can take out at least one x, right? It's like 1, 2, 3, 4, 5, 6 x's. If it's under the 4th root, I can take a quadruplet out of that. With 2 left over inside, the y cubed is kind of stuck, so it's there. All right, that was a mildly interesting type of problem. 79, kind of the same idea. If it's a cube root times a cube root, you can multiply the parts that are inside to one another. So 3 times negative 9 is the cube root now of negative 27. T to the 4 times t to the negative 1. I'm just going to put them side by side. Same with these two, just so we can break it down the best way we should. Since they're side by side, you can just call it 4 plus negative 1, which is t cubed. You get negative 27 over here. Add these together because they're multiplied side by side. That's v to the 6. Everybody's still under the cube root. Now, put it all together. We just talked about how you can divide the power inside by the root on the outside. 3 divided by 3 is t to the 1 power. Completely getting rid of that. This is going to be v to the 6 divided by 3, which is v to the 2. That's gone. And then actually, this is interesting. A lot of people have a misconception that if you see a negative under a root, it's automatically like some kind of weird imaginary number type situation. But technically not with odd roots. You can take negative 3 times negative 3 times negative 3 to get negative 27. This is 9 times negative 3. So the cube root of negative 27 is negative 3. All right, now this doesn't look any different. In fact, it looks easier on 81 and 83. But technically, the directions say simplify the expression, assuming x and y may be negative. Now, if we talk about all the simplification done up to that point, I guess we were assuming all the variables could only be positive amounts that we were taking the roots of. Now, the textbook didn't specify that, but I guess this is sort of like retroactively saying we were assuming they were positive. Okay, so what does that mean? Why is this interesting? It's interesting because of one thing. It seems like this is supposed to be the answer of it, but it's actually not. The answer has to be more specific than that, and here's why. All right. Let's say let x equal 2 and y equal 3. All right, so I'm going to dig into this a little bit. Let's say we're taking the square root of x to the 6, y to the 4th. I just stated that it should equal x cubed times y squared. But I'm doing this with a question mark because I actually know it's not right. But anyway, let's plug in the values and see what happens. No, I'm sorry. Let's not let x equal 2 and 3. Let's let them be, assume they're negative maybe. What happens when they're negative? Whew, almost messed that up. So then I'm going to plug in where they belong and plug them in where they belong over here. So negative 2 to the 6th power. I happen to know that that's 64, all right? And this will be 81. Over here, you've got negative 2 times negative 2 times negative 2. That's negative 8. And negative 3 times itself is positive 9. Now, the square root of 64 is 8. The square root of 81 is 9. All right, so here's the deal. Nothing was wrong with the square root of y to the 4th becoming y squared. There was something wrong with x to the 6th becoming x cubed. It's this idea that if you go from an even power, or an even root, okay, to an odd power, that technically this situation could be lurking in the shadows. And what you do is you say, I'm just instantly going to say, whatever happens here, I got to take the square root of it in order for it to equal what happens underneath the square root. So that's what we're going to do. You put absolute value bars around any odd power that emanates or that comes from an even root. So let's just apply that to this situation right here. And this is a little different. It's got a little extra spice challenge to it. X to the 8 divided by 4. Remember, we can do that. And then we can do that for this entire quantity. Okay, so there's nothing different about it. There's nothing different about it. This is x squared. Now, it seemed it's pretty safe to go from an even root down to an even power. That's fine. No absolute value bars needed. 12 divided by 4, though, is an odd power. So what we do, in fact, actually, when you encounter a situation where parentheses now need to be turned into absolute value bars, you can just do it like that. All right, I'm going to try to squeeze in number 87 and 89, and then we keep it to 3 videos, and we got this thing. All right, the instructions on these two. Actually, I said I'd do 85, 87, 89. Hopefully I'm not pressing my luck. We got just 4 minutes to go, 4.5 minutes. Okay, they say replace the symbol with either equal to or not equal to make the resulting statement true whenever the expression has meaning. Okay, let's try it. So in 85, you got a to the r power squared. And they're saying, do we put an equal there or a not equal to for kind of like all situations? And this is a to the r squared. So they're saying the whole power is r squared. Okay. And then on 87, we'll just put them all up at once here. A to the x, b to the y. A, b to the x, y. All right, so it's kind of like think piece type questions where you really got to ponder. Okay, so for the first one, let's just think about this. What does it mean to be a base with an exponent, the power, the whole thing's a power, taken to another exponent? I mean, like, what would we do if that r were just some random number? Like, what if it's a to the 3? Didn't we just multiply them together? Be a to the 6th power. So we're multiplying r times 2. So it's technically 2r, which is not r squared, right? If we do that plug in again, 3 times 2 would be 6, 3 squared would be 9, and those would not equal each other. Ha! All right, next one. It's kind of hard to tell what to do with the a to the x, b to the y. There's not really much place to go. But on the right-hand side, I can talk about this xy, that total xy, gets distributed to both the a and the b. So this is the same as a to the xy times b to the xy. Which in that situation, it's like, hey, I don't see a y applied to the a, and I don't see an x applied to the b. So it's missing some pieces here. These two statements are not equal to each other. I mean, you might find like one case, maybe two, where the x and the y work out. But in this particular case, you cannot say it works for every single situation. All right, last one. It kind of seems like the right-hand side, I guess I could try to get rid of the root on the bottom, but it's n. Actually, here's how you would do that. It's really weirdly complicated, but not really if you've gotten some more math training under your belt. You need n c's, right? C to the nth power to make this just a regular c on the bottom. So you'd actually multiply it by c to the n minus 1, because you got one of them. Yeah, so it'd be, right, c to the 1 plus n minus 1. Boom. That would actually make c to the n. And then you multiply it up top here. That does nothing for us, though, because this doesn't look like that at all. Here's the thing. Remember how I said you can break up the roots? You remember when I said that. Well, it doesn't matter. Whatever root you take of 1, it's 1. Right? 1 times 1 is 1. 1 times 1 times 1 is 1. 1 times itself n number of times equals 1. So that top is always 1. And that bottom looks just like that one. We have a match. They're equal. All right, guys, I will post the assignment on Google Classroom. Good luck.